Is this all right? This is better? Okay. Well, thanks so much for inviting me to this. I'm really sorry to have missed the first day. I heard it was great. And yeah, it's really lovely to be here. Wonderful city, wonderful audience. I'm sure it's going to be a great conference. So let me kick things off right away because we don't have much time. And I hope we can keep it going in discussion. So as introduced, this is going to be a talk that touches on philosophical topics as well as physics at the intersection. And one of the things that in which I have kind of detected a disparity between the philosophical community and the philosophers of physics, at least, and the physicists is that on some topics, such as the role of symmetries, in physics, people seem much more willing to think about relationism or trying to give descriptions of the theory that don't allow non-trivial action of symmetries, whereas in philosophy of physics, people have a different attitude. So I'm going to start by describing this disparity, and then I will try to bridge the two communities in a certain way. So the talk is called How and Why to Be a Relational. So let us just fix some meaning of the terms so that we are on the same page first. Let's talk about reductionism as the conjunction of two ideas. The first is that the theory uses more variables than are strictly needed. I'm not going to get into what that means for empirical or observations, etc. Just take it as it is. And that we should seek to reformulate these theories with a different set of variables where no such redundancy would persist. Okay? And usually, we think of the redundancy in the original theory as associated to a symmetry between the variables, something that is not empirically relevant. This is it's an oversimplified picture, but here I've tried to depict the space of models of the theory. Oh, I have the pointer. Here I have tried to depict the space of models of the theory. Phi here is a model. I've depicted in orange all the models that are supposed to be related by a symmetry to phi. Here's the orbit of phi. Here's a group, a symmetry group. This is a simplified picture because some symmetries are not given by groups. They're given by groupoids and so on, but this is the case I'm going to treat here. This square bracket here is equivalence class. It's just an abstract way of putting all of these models together into one big set. It's not really a representation. It's a very abstract thing. And this space here, which is blue in my screen, but it's black in yours, is the space of all these equivalence classes of models that are related by a symmetry. Now, finding a set of relational variables, here's what I'm going to mean by this, is a set of variables that describes the symmetry invariant relations between the original variables. That's one approach to reduction. So the idea is that you find some set of variables in which you can actually represent this blue space here one-to-one, this set of square brackets here in a one-to-one manner, right? You don't need to appeal to these abstract equivalence classes. Now, philosophers, ever since Newton and Leibniz, have had a lot to say about symmetries. But I think it is fair to say that the trend, at least since I've been in the field, has moved away from reductionism and relationism. Now, why is that? The first idea that plays a role into this judgment is that any theory will always have some amount of redundancy. So here's John Ehrman, which in his book, he says, the point can be more generally put this way. No theory, written in any standard logical language, whether the underlying logic is first order or nth order, can fix the models more closely than up to isomorphism. Thus, the existence of isomorphic models does not in itself cast doubt on the adequacy of the theory or the existence of the entities postulated by the theory. Of course, there may be something suspect about some particular class of isomorphic models, but the case has to be made on the particulars. Right here, isomorphic models, they're going to be tightly related to symmetry-related models. But the idea is that you can't get rid of some amount of redundancy whenever you express things through mathematics, because you have permutations of set theory, or sets in set theory, and so on, and everything up from there. So when should redundancy become suspect and reduction attractive? This is, I think, fair to say, it's a consensus, or widely endorsed, let's say, not a consensus, by philosophers. It's called sophistication about symmetries, a nomenclature new to Neo-Dewar. Now, suppose again that we have our models, phi, and we can kind of split the structure of phi into two parts. The first part is a fixed background structure. So these are the independent variables of the theory. Could be a smooth manifold for GR. Could also be a vector bundle for gauge theory. And a dynamical content on top of this background. Could be the metric for GR. Could be a section of the vector bundle, or tensors thereof for gauge theory. We write it as a double, like this, the background and the dynamical content in the background. And now, suppose further that this background structure admits a mathematical notion of automorphisms, right? So you start out, let's say, with a smooth manifold that admits a notion of transformations, isomorphisms that keep that structure, keep the smooth differentiable structure. These are the automorphisms. For vector bundle, it would be the linear automorphisms, fiber preserving, that preserve some structure, etc. Then we can say that theory, I'm going to just call them Ehrman's principles here. If and only if its symmetries are just those induced by the automorphisms of the background. So, like isometries are induced by diffeomorphisms of the background, you would have gauge transformations be induced by the linear automorphisms of a vector bundle and so on. Now, one might think, well, this is kind of a trivial condition on symmetries, but it's not so. Here's two counterexamples. The first is in Newtonian theory, a Galilean boost is a symmetry of the dynamics, which is not an automorphism of the background structure. Okay, so that background structure is Newtonian absolute spacetime, and boosts don't respect that background structure. In electromagnetism, in the vector potential formalism, if we take the background structure to be just a smooth manifold and get one forms on top of that, again, a gauge transformation is not an automorphism of that background structure. Of course, in principal bundle, it would be a different story, principal bundle formalism, but so on. But this is enough to say that the condition is not trivial. So what is special about this? The fact is that if Ehrman's principle is satisfied, the symmetry is about which arbitrary part of the background instantiates which dynamical fields, right? Because there's no structural feature of the background that can distinguish between solutions that are related by this isomorphism, unlike in the boosted case in the Newtonian mechanics. So here the idea was that this sphere, I should be able to rotate it, and the idea is just to, well, I can't here, so the idea is that it doesn't really matter if you think of the background structure here as being spherically symmetric. It doesn't really matter how you place the continents, etc., on top of it. You're just choosing arbitrarily which part of the sphere will instantiate which part of the continents and the ocean, etc. I could rotate it any way I want and present to you a different representation of that. And then in these cases, sophistication draws a line. Sophistication says, we shouldn't reduce the formalism of the theory. Once we reach that level of representation of our theories, we don't need to reduce the formalism of our theories. We shouldn't be relationists. Okay? So summing up this part, every mathematical representation comes with some notion of isomorphism, and sophistication gives a criterion stipulating when we should understand isomorphic models as representing the same physical situation. And you don't need to go deeper than that. Now, what's left? Why should we not stop there? What are the defects? First, let me again recapitulate what is the attractive about sophistication is that it allows us to live with isomorphisms, right? To understand the symmetry invariant ontology without requiring symmetry invariant descriptions of that ontology. But then you need to ask yourself, why do so many physicists who agree that isomorphic models represent the same physical possibility talk so much about finding a complete set of observables, for example, a set whose elements taken together, here just very briefly what observables are, and very broadly, a set whose elements taken together distinguish two isomorphism classes of models. That is, any two models in two such classes disagree about the value of some or other observable in the set. Right? And this is a recurring theme. I'm sure it appeared yesterday, and it will appear again. Here is Chris Isham, who talks about the relationship between diffeomorphism, symmetry, and GR, and observables. He says the diffeomorphism group moves points around, and invariance under such an active group of transformation robs the individual points of the manifold of any fundamental ontological significance. The argument is closely related to the question of what constitutes an observable in general relativity, a surprisingly contentious issue that has generated much debate over the years. Although it has also generated debate among philosophers, but I think the consensus is that we don't need to worry about it too much. And of course, there are many more. Carlo, Rovelli, Smolin, Jacobson, lots of people have written about finding observables for GR and the need for doing this. And two philosophers have assessed the situation amongst the physicist community as saying, far from dismissing the whole argument, which is this worry about isomorphic models in the case of general relativity, models that are related, whose metric are related by diffeomorphism, that's called the whole argument in philosophy. Far from dismissing the whole argument as a simple-minded mistake, which is irrelevant to understanding general relativity, many physicists see it as providing crucial insight into the physical content of general relativity. So, what are these physicists after? So, I will now briefly tell you what the defects are that sophistication has and what reason we could have for going beyond them. And then I'm going to tell you about how some form of relationism cures these defects and why that is related to quantization. So, excuse me, what is left after after we accept sophistication? Well, note that sophistication gives no tractable way of distinguishing physical possibilities. Okay? So, for example, in GR, you're given two models. Here I've included matter, just for completeness. M, G, and psi. Psi is the matter. These are two different models. And I don't know if they're isomorphic or not. I don't know if they're related by a symmetry of the theory or not. Sophistication will give you no way to tractably ascertain whether they are isomorphic or represent the same physical possibility. And it also leaves, right, because sophistication doesn't talk about that. It just says you need not worry about symmetry-related models, but it doesn't tell you how to distinguish models that are symmetry-related or not. It just tells there exists some diffeomorphism. It has this existential quantification which is intractable. And it also leaves no way to articulate counterfactuals, such as this region could have been more curved. For this, or at least to do this in a very complete fashion, I want to argue we need some notion of counterparthood, as philosophers call it. So this was supposed to be how, just without the two, how regions of a model in one equivalence class correspond to regions in a model in a different equivalence class. You need some notion of this counterpart relation, right? You need to talk about superpositions of space-time or whatever. You need to represent things in the same space-time, and therefore you need to compare two different solutions and talk about them as cohabiting some kind of region. And so you need some kind of counterpart relation, also to express counterfactual. Okay, so here's the first defect in quantization. I don't think these reasons are usually mentioned, though they may be implicit in why physicists endorse relationism. But as far as I'm aware, mostly relationism comes into the textbooks when it comes to quantization. So I don't think you find much about relationism, let's say, in Wall's book about GR, right? There's some footnote about how diffeomorphic related models represent the same physical possibility, but doesn't really talk much about this. But so here's an example, just for those of you who are more familiar. So for example, when it comes to quantization, you have first-class constraints, and you need to translate that into conditions in the wave function. And that, when you do canonical quantization, that translates into a condition that the wave function should be invariant here. On here, I just took the spatial diffeomorphisms, or the supermomentum constraint. So you just see that the wave function needs to be invariant under those diffeomorphisms. And that gives you a reason to think, well, OK, let's now try to do this explicitly and find variables for which this is automatically implemented. Now, so this certainly has to do with the first defect, that we want to have a unique description for the isomorphism classes, such that given two unique descriptions, it is obvious either they are identical and they correspond to the same isomorphism class, or they're different, in which case they're different, correspond to different isomorphism classes. And technically, I think this can be understood in terms of either in the terms of the Dirac constraints or avoid overcounting in the path integral and so on. Now, here's one puzzle that you might consider is, well, a conceptual puzzle. Why does quantization require reduction or relationism at a seemingly more fundamental level than classical physics would? So let's move on to the second defect. Here's a quote and the second defect, if I may remind you, is that sophistication doesn't really it doesn't really give you any handle on how to compare models that belong to different isomorphism classes, okay? Models that would be physically distinct. Here's a quote by Penrose that encapsulates this idea. He says, "The basic principles of general relativity, as encompassed in the term of the principle of general covariance, tells us that there is no natural way to identify the points of one spacetime with corresponding spacetime points of another." So this is this lack of, once you give away this idea that the bare points of the manifold have some independent significance, you can't really compare. You can't really say, oh, the metric at point X is such, and in one model, and the metric at point X in another model is so-and-so. Because that comparison means nothing, because the point X has no meaning if you adopt sophistication. Right? Because sophistication tells you, once again, that it's arbitrary how you're putting the dynamical content on top of the background structure. So at a more conceptual level, I want to say that relationism is necessary for being explicit about counterfactuals, for example, as used in the initial value problem, or for superpositions of states of semi-classical descriptions, as we did recently in a paper with Chaslov's group. So, but how can the two gaps or the two defects be related? How can finding a complete set of observables dealing with the defect 1 help with the defect 2? Right? So here it depends. One often hears that space-time points can only be individuated by their sufficient rich properties in relations to other space-time points. This is a very common trope in philosophy of physics and even in physics. So the idea here is that we're going to give you sufficient relations such that using these relations you can talk about a point satisfying them in one model, or a region satisfying them in one model, and a region satisfying them in a different model. And then we can compare, relative to these relations, the content of the two models. But one should be a little bit careful here, because you can suppose you single out a point as the unique one with values 1 to 10 for 10 functionally independent scalars formed from the Riemann curvature. Now, these may give you a description of a region, but they can't be used to express interesting counterfactuals, at least about the metric. Because once you fix these 10, nothing about the curvature can vary in respect to a different model. So it will have to all be the same in different in that region. So what you want to do is have, in this case, such regions or curves described. You're over-constraining the description. And they bear so that the regions and curves so described bear their content essentially. Right? You want to be loose enough so that you can still talk about different dynamical contents in the same region, so to speak. So we're looking for descriptions of regions that are maximally constraining with respect to location, but minimally constraining with respect to physical content. Okay, so this leads me to representational schemes. Now, I'm going to introduce that through gauge fixings and what has been now commonly known as dressings. We can fix what I'm calling a representational scheme here using an immersion of the space of equivalence classes into the full space of models with their redundancies. It needs to be an embedding such that intersects each orbit exactly once. Now, the immersion is most easily described as a regular value surface. I'm not going to describe this in detail. It's straightforward. And the idea is that you should be able to obtain a solution for this condition here. So basically, given any model, I transform the model through a gauge transformation. This is what I'm calling or a symmetry. This is the subscript here is I'm acting on phi with a symmetry that I'm calling omega of phi. Right? So this is a function that takes any point in the space of models and brings it to a group element. Okay? So it's a group valued functional on the models. And it has to be such a functional that taking any model and you apply this symmetry transformation to it, it will transform this model here into a model that belongs to the surface that I established. Such that, so this is the condition, mathematically speaking, this needs to have a unique solution for all phi. Okay, for this, you can solve it uniquely for this functional here. And we call this functional, that's group-valued functional in the models, a dressing. Now, it follows that the dressing will obey a covariance equation, so that if you apply, it's kind of trivial to see in the geometric picture, if what the transformation that is taken to transform this from here to here, and the transformation that it takes to transform this from here to here are related by a transformation of this from here to the middle point here. This is what it says, essentially. Right. Now, this is interesting because if we define H as this dressed version, or a projection, for any f, this will give you a symmetry invariant function. Now I'm just writing this, I'm defining this function here as the dressed model. And you can check that if you transform this phi and this phi, you don't change. You get the same dressed model. Okay? So given this gauge fixings and these dressings, we obtain a description of the state that is completely symmetry invariant. It's true that this description satisfies the original gauge condition once you have this dressing, but we don't need to mention f anymore. This gives me, and I can give you examples, gives me an explicit symmetry invariant description of the state that provides a tractable condition of individuation or individuation of physical possibilities. But it still depends on a choice, right? So there are many such choices of dressed variables, at least one, each corresponding to a gauge fixing at least. But I don't need to talk about gauge fixing. I'm not breaking the gauge symmetry in any way. This is a completely symmetry invariant description. It depends on a choice. I call it representational schemes to dissociate with this idea of gauge fixing, that you're breaking the gauge, but it's not a significant distinction. Now, there is a sense in which this addressed function is relational, because the functional usually compares values of all the components of the model. It satisfies certain functions, and it compares different values of the models at different points, for example. And usually this value, this address functional, will be non-local, but I'm not going to get into that too much. And it can also be interpreted as a description of a state relative to a physical reference frame. Now here are some examples of physical reference frame. Here's harmonic gauge, which is equivalent to 4 massless Klein-Gordon scalars satisfying wave equations, and it can give you locally a symmetry invariant description of the metric field, for example. And unitary gauge can also be interpreted as giving a nowhere vanishing section of a vector bundle with respect to which you can describe any other state invariantly. So it gives you, this is a relation between these gauge fixings. I gave you a relation between gauge fixings and dressings. There's a relationship between these gauge fixings and reference frames, right? Just 2 examples. Okay, so now finally to counterpart relations. This is a section, as I described it. And given a 1-parameter family of non-isomorphic spacetimes, this is in the blue here, we can project that curve down to the section in which it started. So here is a family of spacetimes, different regions, M3, M2, M1, corresponding to 3 points along this line. And I have described the metric in a certain way. But when I project to it, I reshuffle, I apply diffeomorphisms at each one of these points. It reshuffles these regions so that it gives you a relationship between these 3 regions that is appropriate to the section, appropriate to the relations that the section has chosen. This projection then yields a 1-parameter family of diffeomorphism, and this is how we thread the spacetime points of non-isomorphic models. Mathematically, you can really write a counterpart relation. Thus, basically, you compose the dressings of any model in here and any other model there, and you get a diffeomorphism that relates the descriptions of the 2 models, even if they are non-isomorphic. And it has some nice properties that if the models happen to lie in the same orbit, then their relationship, the counterpart relation, is just given by the diffeomorphism or the isomorphism that relates them. Right. So let's wind down. A representational scheme answers point coincidence of what? So which structural qualities are you choosing? Depends on the gauge fixing or the dressing that you have chosen. And it will give you a criteria of similarity between counterparts in different spacetimes. And it does allow us to represent superpositions of spacetimes. But these superpositions will depend on the representational scheme. This I have not shown you. How much longer do I have, Jeremy? Okay, then I won't. But the interference, even though superposition depends on the representational scheme or on these ideas, interference between semi-classical states, etc., shouldn't depend on it for the 3+1 fixed foliation states, fixed and classical solutions. Here are some leftover puzzles, apart from that initial one that I started out with. As with gauge fixings, we choose representational schemes in order to shed light on certain properties of the models. Right? At least this is the idea, that you need to fix the representational scheme or the gauge fixing, having in mind either an observer or some apparatus or some kind of feature of the models that you want to highlight. Other properties, when you do that, may retreat into murk. Now, which properties will depend on the context of application, and they will often involve some indexical element relative to us or a particular physical reference frame that we set up. Now, I have given you 2 examples of this relationship between physical reference frames and gauge fixing or dressings, unitary gauge and harmonic gauge. I very briefly talked about them because these are the only 2 examples that I very clearly understand. And so one question that pops up is, can we always find a definite instantiation of the gauge fixing as relative to a physical system? Because you see, the gauge fixing, as I said, it gives you control over when you are stipulating just enough counterpart relations to not limit physical content. So it would be used, and you understand, moreover, I didn't write down the conditions here, but you can understand transition functions that are non-local depending on the field, etc., but they depend only on the orbit between different gauge fixings. So you have very much under control how to translate between different descriptions in gauge fixings. Where for other kinds of observables, it's not clear to me how you can always translate. And this is something that I've talked a lot with Daniele Odici, who's not here. So one idea would be, can we always find a definite instantiation of the gauge fixing as relative to a physical system? And then there are all kinds of follow-up questions that pop up once you're able to do that. Can we interpret limitations of the physical system in terms of the Gribov obstruction? Because any physical reference frame can fail at some point. It can develop singularities, caustics, etc. Can these be interpreted as limitations related to the Gribov problem in gauge theory, which tells you that there's no gauge fixing for non-abelian theories that would cover all of the configuration space of the theory. Now, most of these gauge fixings are local. They fix a coordinate system on a patch. And so, for instance, for massless scalar fields, we'll hit caustics. And there are global versions, let's say, of harmonic gauge, but they usually require auxiliary metrics and can't be interpreted in terms of physical reference frames. So this is another question. It seems that only local or gauge fixing conditions can be interpreted as physical reference frames, which might be, well, interesting in terms of the physical characteristic that they embody, but there's also this distance between the full application of gauge fixing in these theories. All right, thank you very much for listening.